So my talk is going to look now at 4G and take a view as to what a 5G world may look like, what are the important technologies and where are we heading from a 5G perspective. So the first question is, why 4G? And I think Julian certainly started to answer this question when he talked about continued data growth over the coming years. You can see now, if we take a snapshot of what's happened from the launch of mobile data, so where Stuart came into play earlier really, talking about 2.5G or GPRS, and then of course we evolved that with Edge to give us higher data rates in that 2G world. We evolved 3G as Errol talked about with HSPA, HSPA+, so some tens of megabits per second available on the 3G network, and then we launched 4G services. So you can see as we increase the data rate, the data capacity increases. We also reduce the latency, so the level of interactivity with the applications increases too. And these things kind of produce a kind of perfect storm, which drives ever more data consumption, of course. The football example Julian gave was excellent. You know, it is really good to stream video content on 4G. A lot of 4G networks now are reporting that over 50% of the data traffic on their networks is in fact video today, and that's expected to increase still further. So that suggests that we're going to have to start building mobile video distribution networks that support data services and voice. It's a different way of thinking about the kind of networks we're going to build moving forward. So what is 4G? Well, it's based on a technology called LTE, long-term evolution. It was the name of a project originally. It's become a brand in its own right now. And again, it came from 3GPP, the third generation partnership project, as we've seen now as the international standardization body that delivers the telecom standards. There's an LTE Advanced specification as well, and we'll look at that through the presentation. But what is it? Well, actually, the term LTE, as I say, refers to initially a working group set up within 3GPP. It was a plan first conceived in 2004. Actually, that's quite an important point because it takes some years to develop these international standards, typically up to a decade to develop a standard and bring technology through to marketplace, which means me talking about 5G is a perfectly valid thing to be doing, of course, as we start to develop that technology over the next number of years to bring it to market in the next decade. But the plan was conceived in 2004 and it was really driven by operators. So operators were very influential in the standardization of GSM, less so in UMTS, but most certainly in LTE. And there were some clearly defined performance targets, some economic targets, some requirements for improved use of radio spectrum, and a simplified system design. 3G was incredibly complex compared with 2G, and LTE is a much simpler technology. You can actually tell from the number of pages that make up the standards release as to how complex the technology is. So, on terminology, now LTE has become the common term for 4G. But actually, if you're reading the textbooks and want to understand what LTE is, you'll come across lots of different terms. LTE originally referred to the actual radio interface itself. So an evolution of the UMTS terrestrial radio access network to this evolved access network effectively. There's also another term you'll come across in the textbooks referred to as SAE, system architecture evolution. So this is the term used to describe the evolution of the core network itself. And strictly, the entire system is known as the EPS, the Evolved Packet System. But as I say, the marketeers have took over. The term LTE has become a brand in its own right. And when people refer to LTE now, they're not strictly referring to an evolution of the radio, rather the entire 4G system. But if you're reading textbooks and you're having technical conversations, it's worth being a little bit careful about the terminology and context, because some people will use it in a fairly pure way at times. In terms of system specs, what did LTE ever do for me? Well, it gave us increased peak and average data rates, and those peak and average data rates continue to grow now with LTE Advanced. It gave us scalable channel bandwidths. This is really interesting. So there's lots of things introduced in 4G that we never had before. So we had fixed channel bandwidths in GSM, in UMTS. We can now use different channel bandwidths, which means we've got more flexibility as to where we find spectrum. In the panel earlier, Stephen Temple alluded to the point that we've got multiple bands. There's over 40 frequency bands available today, and the number's increasing all the time for LTE services. And that brings some challenges in its own right in terms of supporting such a diverse range of spectrum on a given number of devices. But nonetheless, it allows us to find spectrum and bring spectrum to market, new services to market in different ways. Spectral efficiency improvements over Release 6 HSPA, which was the benchmark at the time, of typically 3 to 4 times in the downlink and 2 to 3 times in the uplink. And I think one thing that's particularly interesting about 4G is the uplink is marketable. You know, we can start to develop and productize the uplink. Whereas the uplink really, historically, the connection from the mobile phone to the network was in a 2G network, 2G data network, there to send things like HTTP GET, TCP ACKS. So it was there to make the process of accessing the web work. In 3G, again, it was always fairly low speed. We started to see HSUPA, high-speed uplink packet access, give us some option for optimization and productization of the uplink. But really in 4G, we can start to look at developing uplink-based products as well. An example of that is an outside broadcast team with a HD camera, 4K camera in the future, with a number of SIMs in, and you can actually transmit from the outside broadcast environment back up to a TV studio rather than deploying a satellite truck. And we've actually sold those kind of services in the UK. We wanted lower latency as well. I talked about things being more interactive before. So the spec for the radio was looking at sub 5 milliseconds latency for small IP packets. Overall system latency, if you do a ping to a server on the internet, is generally between 40 and 60 milliseconds. You know, that's maybe 20 milliseconds less than it is on HSPA, and probably 40 milliseconds less than it is on the original 3G standard, and over half a second faster than it is on GPRS, of course. And we wanted coexistence with legacy standards while evolving to an all IP network as well. So we have to work with 2G and 3G. We have mobility in and out of them, but they're very different networks in many ways. So how did the story start in the UK? Well, it started with Ofcom approving the refarming of 1800 megahertz spectrum, which is a request that EE submitted back in 2012. Now, this term refarming simply means repurposing the use of spectrum from one particular technology to another. It's going to become a fairly academic term in the fullness of time, because now we have a level of spectrum neutrality, and we can use, as an operator, you can use the spectrum assets for 2G, 3G or 4G. And it wasn't a new concept when Ofcom approved this refarming for EE. It had previously approved refarming of 900 megahertz for O2 and Vodafone to use that spectrum, not for GSM, but for UMTS 3G services. So it's going to build in on that concept. But this really did drive the 4G ecosystem in the UK. Now, the UK is often regarded as having been a laggard in 4G services because of delays over the auction and various politics that went on. But actually, the UK entered the 4G market just as 4G smartphones were becoming available. Those early adopters elsewhere had 4G available, but purely for dongles and mobile Wi-Fi devices, etc. So smartphones started to evolve in 2012. And the lineup you see there is the lineup that was announced just prior to EE's launch. And you'll notice, you know, it's a fairly limited number of handsets. There were just 6 handsets in the world at the time that would support 4G on the 1800 megahertz band, which is a spectrum that had been refarmed to support the service. There was also a dongle and a mobile Wi-Fi device. What happened the following day really did catch people's imagination though. The iPhone 5 was launched the day after these products were announced, and the iPhone 5 would support LTE in the 1800 megahertz band. And suddenly, something really exciting was starting to happen now. We're starting to get 4G across a whole range of top-end smartphones, from the Samsung, HTC, Nokia and Huawei devices we've just seen, right the way up to the iPhone as well. And of course, the iPhone brings with it its own market of fully dedicated Apple fans. So, when did it land in the UK? Well, the 30th of October 2012 was the official launch of the UK's first 4G network. Big launch event. You can see Battersea Power Station there, which is illuminated as part of the event itself. But actually then what happened was we had another spectrum auction. And had I been talking about 3G, I wouldn't have been able to put the prices up because I wouldn't have fitted them on the screen. But thankfully, in the 4G auction, the prices were somewhat more sensible. Each operator went in with their own strategy to source spectrum based upon their own requirements. And as somebody correctly pointed out earlier, BT purchased some spectrum to become an operator in their own right once again. So here now we see the different spectrum bands. The spectrum that was auctioned in that particular process was in the 800 megahertz band. So that was spectrum that had been freed up after the digital switchover. So previously digital TV spectrum, or analog TV spectrum, sorry, that was freed up once we moved TV to digital. And spectrum in the 2600 megahertz band. Now interestingly, Graham mentioned earlier that when we talked about building networks at 1.8 gigahertz, it seemed a fairly crazy idea in the early 90s to build a national network at 1.8 gigahertz. 900 megahertz was considered to be a high frequency at the time. And now cellular is going up to 2600. Now 2600 spectrum will be used in a very different way to 800 megahertz spectrum. One will give you wide area coverage, good in building. One will give you loads of capacity in urban hotspots and pushing out to the suburbs and certain other use cases. So we've now got operators, 5 operators with spectrum, 4 of them of course being the established operators, and therefore 4G becomes really competitive. We see increased advertising from O2 and Vodafone, who launched on the same day in August 2013, followed by 3, Errol mentioned, 3 switched on 4G without any additional tariffing, and that was launched in December 2013. Now of course each operator is rolling out in their own timeline, and the coverage varies from one operator to another. But what is a 4G network? I said it's very different to 3G and 2G before it. It's very different because we don't have a traditional telephone network. We started off with TACS, and TACS was about mobilizing the telephone. It was all about voice telephony. And slowly we introduced this parallel data network in GSM. We enhanced that data network in UMTS, but we still had our traditional circuit switch telephone network. We don't have that at all now. So we really are moving to a true IP network, which means we need to run voice over IP. Errol again mentioned the term VoLTE before, voice over LTE, so it's a variant of voice over IP for the LTE network. But initially, actually, everybody launched 4G with a mechanism called circuit switch fallback, where you would drop back onto the 3G network to make a traditional voice call, and if 3G wasn't available, you'd drop back to 2G. In the next year, you'll see all the operators launching voice over LTE services, and eventually you'll see that circuit switch network being phased out. But actually, to make that happen, to connect to the PSTN and other licensed operators and make calls, we add even more technology into our network. A thing called IMS, the IP multimedia subsystem, which is a control plane entity. It controls a number of media gateways, allows you to introduce a number of different protocols, and also it gives you a service creation environment. So you can open up APIs at the top of this and develop a whole range of new and interactive location-based and messaging-based services. So quite an interesting environment now for the operator to be working in as we introduce quality of service on these packet data networks. 4G deployments. We're seeing lots of new equipment, and we haven't talked too much about the network side today. We have got some network equipment outside, but every time an operator introduces a new technology, there's lots of truck rolls, there are millions and millions of pounds worth of investment, and clearly there's a project timeline to get that infrastructure out into the network. So here's an example of a single RAN platform. There's a picture of the equipment inside this on the networks desk, and here this base station is actually running 2G and 4G on the same platform. It's actually running 3 different bands of LTE, this particular base station. It's running LTE at 800, at 1800 and at 2600 on this particular site. The 2600 installation uses a remote radio head, and there's an example of it. Because it's such a high frequency, you want to get those radio heads as close to the antennas as possible. So we run an interface from the baseband capability in the cabin up to the radio itself, which is close to the antenna. Antennas themselves are becoming increasingly complex now. Here's an example of an 8-port antenna. That particular antenna supports 2G, 3G and 4G. It supports 800, 1800, 2100 and 2600 megahertz. So 4 bands, 3 radio access technologies on the same antenna. Now, strictly, of course, as an engineer, that's 8 antennas. It's not 1 antenna, but it physically looks like 1 shroud. It looks like 1 antenna, but actually, of course, it is 8 antennas. And of course, now we've got a very diverse range of devices, from dongles to mobile Wi-Fi devices, home routers. Again, the fact we've got this really high capacity network, both in the downlink and the uplink, allows us to offer alternatives to DSL in areas, for example, where superfast broadband may not be available, areas where standard DSL services are potentially quite poor. We can target certain rural communities with these services, and we're selling these services in Cumbria, for example, and a number of other areas. Tablets. Now, tablets, of course, when dongle mania kicked off that Julian mentioned, all the kids were buying laptops. Laptops were really commoditized, low price. You stick a dongle in the side of it and you can get online. Now, of course, we're seeing laptop sales drop off in favor of tablets. The tablets now have integrated cellular. So you've got Wi-Fi on there, but you've also got 4G available on the tablet as well. And in-car Wi-Fi, this is a huge market taking off now as well. You plug this device in your car, it's got power. It gives you a USB port on the back, you can plug in and still charge things from it, and it gives you Wi-Fi in the vehicle. If you've got 3 screaming kids, there's suddenly 3 quiet kids, because they've got Wi-Fi and connectivity whilst travelling. So a whole range of new services, and there are cameras now, action cameras you can buy that you pop onto your cycle helmet that will stream content in real time to a server, for example. So a whole range of applications. We're just starting to really understand what we can do with 4G. The technology is evolving all the time. I mentioned LTE Advanced. LTE Advanced is being implemented now in the UK, typically in terms of carrier aggregation, where we take multiples of these channels, be they 10 megahertz or 20 megahertz, and we aggregate them into a virtual channel that is of wider bandwidth and can therefore offer much higher data rates. We've seen demonstrations of data rates exceeding 400 megabits per second on UK networks. The UK mobile 4G networks are now amongst the fastest in the world. So from laggard to world leader, the UK has more mobile subscribers than most other European markets. In fact, we're number 1 in Europe. EE is number 1 operator in Europe for mobile subscribers on 4G by volume. Whole range of technical developments to come yet, including MIMO refers to the antenna systems, how they're going to evolve. Heterogeneous networks I'll talk about in a moment, and a whole range of other technologies. But let's just dig into that story of HetNets. So we offer higher peak and average data rates, but actually people start to consume ever more content, of course. So we need to be able to constantly scale the capacity to meet that demand. And the actual shapes in the background, though, are not mountains. Rather, what I'm trying to indicate there is the coverage from a macro cell and a micro cell. So as you move away from the cell, the data rate you can achieve starts to drop off. So there could be certain scenarios where you want to put some small dedicated cells in to enhance the cell edge experience, for example. A lot of data usage is in building, so you may want to put dedicated solutions in building to take that traffic out at source rather than use a macro cell, particularly if you want to reduce power on networks, because obviously there's a lot of attenuation to get from outside into a building, whereas actually if you have a solution in the building, then you can use that power for other things outside. And ultimately, we'll see hotspots and small cells as underlay networks, areas of contiguous small cell coverage, giving us ever higher capacity in mobile networks. And this is certainly a part of the 4G standard. It was never really built into 3G before. That's why you never really saw small cells take off in great volumes in the 3G world, but it's certainly a key part of the 4G standard. So that's something to watch for, an interesting technical development. So a few words about 5G as we start to bring this towards a close. There is an objective for 5G that's been defined at the University of Surrey at the 5G Innovation Centre, And the objective is to provide always sufficient rate, that's referring to data rate, to give users the perception of infinite capacity. Now clearly as engineers we can't build networks with infinite capacity. But actually if a subscriber wants 10 megabits per second, 20 megabits per second, 100 megabits per second or 1 gigabit per second, and they get that wherever they are, whenever they need it, of course they have this perception of infinite capacity. And that's exactly what the research is driving towards. What kind of research goals? Well, these are still being debated. Different people will give you different answers, but to give you a feel for the kind of dialogue in the industry, most certainly higher peak and average data rates. But actually what we really want is much more capacity, area capacity. It's a slightly different thing. But nonetheless, peaks of 10 gigabits per second have been talked about. Average of 1 gigabit per second with minimum service levels of 100 megabits per second. So, seems very, very ambitious. 15 years ago, we were launching GPRS, and if we were getting 20 kilobits per second, we were partying. You know, this was rock and roll stuff. So, yeah, this is a technology that'll be really maturing in 15 years from now. So, it's not too unreasonable. Ultra low latency, less than 1 millisecond for certain services, less than 10 milliseconds as the norm. Why would we want particularly low latency? Whole bunch of applications there. The one that's held up often is kind of remote surgery and that kind of thing, which is a fairly extreme use case. But I think vehicle to infrastructure and vehicle to vehicle is a real use case. So collision avoidance, pre-warning other vehicles of hazards further down the road, etc. Some interesting use cases around that, and interesting to see the example Mike showed before of the smart car in Greenwich and the work that's going on there as well. Ultra reliable networks. So mobile, when it launched, was a novelty. It was fantastic. You could make a phone call outside. How cool was that? But actually, over time, it's become ever more critical. And if we want to move into new vertical markets with mobile services, we have to ensure ultra reliability wherever, whenever, and whatever. So again, lots of work being done in the research community on this topic. And energy efficiency. ICT globally is consuming ever more power. If we want 1,000 times more capacity, we can't consume 1,000 times more power. One of the design goals of 5G is to offer 1,000 times more capacity without consuming any more power than we're doing today. So again, big area of research. Excuse me. And then massive device connectivity. You know, we've not begun to connect anything like the number of devices that can be connected to networks in the future. Everything that can be connected will be connected. So there will be a massive density of devices in every area connecting through the internet of things, machine type communications, etc. And that will include, as I say, cars talking to cars talking to infrastructure. If you're driving to a set of traffic lights, the traffic lights are on red, there's no other cars on the road, why do you need to stop and idle? Surely the car can say, is there anybody else around? The traffic lights say, nope, off you go. You know, it would make sense. It reduces emissions. It speeds up the journey. It's generally more efficient for everybody. So you think about those kind of strategies which are really tying together the evolution in mobile communications with big data and data engineering. And you think of the opportunities for multimedia services as well. There's a huge number of opportunities around the wider Internet of Things. So what will 5G look like? There's a paper there in your guide that tells, in your delegate pack, sorry, that tells you a little bit more about 5G. But how do we achieve it? Well, 5G should start to see the end of 3G and 2G networks. 4G will be the underlying infrastructure that has national coverage, and 5G will start to build on top of that. Evolved Wi-Fi has a role to play, either directly in cooperation with cellular, a system that's being developed now, or as an alternative network that connects into the cellular infrastructure as well, similar to the voice over Wi-Fi services that we see today. And some of the key research areas, I'll go through these fairly quickly, but happy to take questions on the panel. Ultra high capacity, we've mentioned, maybe starting at 1,000 times more capacity, increasing to 5,000 times more capacity over the lifetime of the technology. Separation of control and user plane, again starting to question some of the models about how we control devices. Maybe we keep the control on one of those big macro cells and just push all the user traffic through a small cell layer. Reduces the amount of signaling for mobility and you start to get the best of two worlds. On-demand services get instant access to services, ultra-low latency for a whole number of reasons, energy efficiency, application awareness as well. So again, the type of service you get from the network depends on what you're asking the network to do. And that allows us some statistical multiplexing gains and benefits from a network perspective too. Device to device, now this is an interesting area. One phone talking to another phone without talking to the network, or a car talking to another car without talking to the network. So there are issues to address here, particularly when you do device to device via device as a relay. But nonetheless, these topics again have been researched, and some of the issues around how these things would fit in a regulatory framework are starting to be addressed. The conversations are happening. Ultra reliability we touched on. Seamless mobility between 4G, 5G and evolved Wi-Fi. We'll not be developing mobility, I wouldn't suggest, between 5G and 2G. It's not going to be the place you want to be. We're moving into a different world here. In building coverage, we have to crack that, and the best solution is to get things inside the buildings. So again, we need to develop to a different model. You wouldn't build a building today without gas, electric and water, for example. So how do you tag in the communications infrastructure there? And actually do new tall buildings have antennas built into the outside of the building that are actually invisible but are available to operators to use? So lots of different thoughts about different business models here. Network functions virtualization and software-defined networks. We're going to have the flexibility to move capability in 2G, 3G, and to a certain extent 4G. Networks are quite static. It's the same network in central London as it is on an island, remote island in Scotland, for example. Now there might be more capacity in one place or the other, but it's the same split of functionality and cost. Whereas actually we could start to change that and make it a little bit more dynamic. We could build a lot more resilience, a lot more flexibility into these systems. New waveforms, we definitely need new and more robust waveforms for certain applications, as well as new spectrum. Always sufficient rate, we mentioned. Wide area coverage and ultra-dense networks are two extremes. Has to be available everywhere. A basement in a remote location to support an Internet of Things device has to be connected. In the centre of a dense urban area with thousands and thousands of connected things, it has to operate. So you have to work in those two extremes. So again, makes you start to think about optimizing solutions to the environment, maybe rather than trying to address everything with the same. New spectrum we touched on, including right the way up into the millimetre wave bands. Ultra high definition video. Increasingly, we're seeing consumers and devices supporting 4K now. Consumers want 4K, they like the clarity of the video. But actually, from an operator perspective, the move from standard definition to high definition to 4K video, it drives ever more traffic on the network. And for the consumer, it's still video content. So they just watch Wayne Rooney's 50th goal on the video device. They don't necessarily perceive the additional value of that being high definition over standard definition, but actually there's an additional cost to carry that traffic on the networks. Stadiums and hotspots, so areas where we really have massive density of traffic. Internet of Things we've touched on. Full duplex radio. So here we really are starting to push the boundaries of what we thought was physically possible some years ago, transmitting and receiving on the same bit of radio spectrum in the same instance. So interesting research areas. Massive MIMO, even more antenna systems. Security, privacy, all these kind of issues have to be addressed. Some of them are potentially generational and will become less of an issue naturally as people get used to being online. Others will need to be addressed at source. SON, self-organizing networks, these are massively complex networks now. We can't actually adjust each individual parameter for each individual site. We have to have feedback and the network optimizing itself, and also working around faults to give us the ultra-reliable network. And then the last one in here, sharing, which will include new business models as well. So again, working with other third parties to understand how best to enable the digital connected society that will keep the UK ahead and set us up for a whole host of new business models and new opportunities. That's my presentation. Thank you very much. So a very short summary. 4G is the start of true mobile broadband. It's IP-based multimedia communications. Demand's huge, and it's going to keep on growing for the foreseeable future. Mobile operators will continue to evolve 4G. 4G is a technology of choice now. That's where mobile operators are putting most of their investment, and that'll increase speed, capacity and enhance user experience. 5G is research, but we're starting now to see some interesting demos and some bold claims. But 5G will complement 4G networks. It will grow off the back of 4G. We'll support ultra-dense networks, higher peak and average data rates, low latency, to enable a tactile web and immersive real-time video. The tactile web, so introducing the concept of touch over networks, haptic feedback. How do you code that haptic feedback and actually experience that as a user as well? And what new opportunities does that open up in telemedicine, for example, as well as a whole range of other industries? From a speed perspective, it often catches the headline. 4G in the standards can take us up to 1 gigabit per second. If you want to go faster than that, 5G is going to come along in the future. So thank you very much. Cheers.